Welcome back to my channel, where you, me, and my houseplants will have some fun doing math. Today we're going to continue looking at limits, and specifically we're going to talk about the continuity of a function in terms of the limits. So we'll start by looking at some graphs. Here I have graphed the function x squared minus x minus 2 all over x minus 2. If you recall, or if you watched my previous videos on limits, you'll notice that this is a function we've already seen, and we were able to take the limit as x approaches 2 even though we couldn't actually plug x equals 2 into this function. We saw that the function actually looks like a line with a hole in it. So I encourage you to go and graph that yourself, but now I've done it here. So this value of a, this little a, is my slider for different values of x. So as I slide a to minus 4, then I'm plugging in minus 4 to my function, and big A is going to give me the coordinate on the graph. So I've coded in here that big A is x equals a and y equals f of a. So I'm sliding along this function. So we can slide a along, and we want to look at what happens when we get to 2. So did you see that little glitch there? Did you see what happened? If I slow it down, it might be more clear. As I'm approaching 2 from the right, it disappears for a second and then it keeps going. So what's happening there is I actually have a hole in my domain. So there is a hole. If we zoomed in far enough, we would be able to find a hole. The reason that we can't see on the graph is that hole is so tiny, it's infinitely small. Because remember, we can plug in values of 2.000001, and we can plug in values of 1.9999, but we can't plug in values of equal to 2. And so we say that this function is not continuous because we have that hole. Let's look at another example of a discontinuous function. So here I've plotted g of x, and I have b that's going to run along my graph. And as I play a, as I move a along, move it faster here, because we can see where that jump is going to happen. So we can tell just by looking at this function that it's not going to be continuous. So you may have learned that a function is continuous if you don't have to lift up your pen when you draw it. That's kind of a hand-wavy definition we give before we have our proper definition using limit. The limit as x equals 0, as x goes from the left, is going to be equal to 1, but as it goes from the right, it's going to be equal to minus 1. So because those limits don't agree, we would say in this case that the limit of this function g of x as x goes to 0 does not exist. We'll look at one more example here. I call this function h of x, and in this case, as I play my value little a, we notice that from the left, as I go towards the value of 1, it drops down, and all of a sudden it appears up here. So let's even slow that down a bit. So we can see we're going towards a value of x equals 1. We can watch our little a get larger and larger, and my y values are going down. So I quickly kind of fall down that hole. So these are 3 different types of discontinuities that we'll find. The first one we're going to call a removable discontinuity, and we'll look at an example of why we use that word. The second one, the blue one we have here, we're going to call a jump discontinuity because it was almost like that value b, that big B, was jumping from one line to the other. And finally, for our orange function, we're going to call that an infinite discontinuity because our values go off to infinity. This brings us to our definition of what it means for a function to be continuous. So we say that a function f is continuous at some number a if the limit of f of x as x goes to a is equal to f of a. Now, this is implying 2 very important things, which means that we will have to check a total of 3 things. First of all, that a is in the domain, because it doesn't make sense to talk about f of a if a is not in the domain. Second, we want to make sure that the limit exists, because it doesn't make sense to talk about the limit of f as x goes to a equals something if the limit doesn't exist. So the limit has to exist for it to equal a value. And lastly, we need to check that there is equality there. So number 3, the limit of f of x as x goes to a is indeed equal to the function evaluated at a. So let's look at an example. In this example, we'd like to find a number c that makes f continuous. So this is once again the function we looked at before, where x squared minus x minus 2 all over x minus 2 is the function we're interested in. But now we've written it as a piecewise function. So we would like to figure out what value of c should I make my function equal to when x is equal to 2 so that I have a continuous function. So first of all, we already know the limit. The limit as x goes to 2, it exists, that's important, and the limit is equal to 3. And so if this function is to be continuous, we need that the limit as x goes to 2 is equal to f at 2. Now originally our function, we said that 2 wasn't in the domain, but now we've created a new function, which is a piecewise function, which has a domain that includes 2. So we can now plug 2 into our function, except now we will get a value of c, because that's the new rule for when x is equal to 2. So for this function to be continuous, we must conclude that the limit of f of x as x goes to 2 is equal to c. And since we already know that the limit of f of x as x goes to 2 is equal to 3, we get that c must be equal to 3. Thank you for joining me. I hope you enjoyed this video, and I look forward to doing some math with you again soon.